In 1993, three engineers squeezed into a Denny's booth in San Jose to plan a gaming chip company. Their first product flopped. By 2002, they had less than $200 million in cash and were circling bankruptcy. Today, that company controls 80 to 95% of every AI training chip sold on Earth, commands a $3 trillion valuation, and sits at the center of a geopolitical standoff between the United States and China. Nvidia may be the most dangerous monopoly capitalism has ever produced, and it traces back to a single bet no one on the board wanted to make. The company began as a gamble at a Denny's booth in San Jose, but the first roll of the dice landed hard. Nvidia's debut product, the NV1, tried to be everything at once: two-dimensional and three-dimensional graphics, audio, even Sega Saturn controller support. By 1996, the market had spoken. Major PC makers passed, Sega abandoned the platform, inventory piled up in warehouses, and the company's first bet became a $7 million loss. Revenues for the year barely scraped $13 million. Jensen Huang, Chris Malachowski, and Curtis Preem pressed on, but the company was running on fumes. Nvidia's survival depended on a single audacious proposal: to outspend the competition and build a chip that could render three-dimensional graphics in real time. Hardware-accelerated transform and lighting, something no rival had attempted. The GeForce 256 project would burn through $400 million in research and development, more than the company's entire annual revenue at the time. Board minutes from 1998 show a split. Several directors warned that the outlay could bankrupt the company. Others, led by Huang, argued that the risk was existential. If Nvidia failed to leap ahead, it would be crushed by ATI and 3DFX. The final vote was razor-thin. The decision to greenlight GeForce 256 locked the company into a high-wire act with no safety net. When the chip launched in late 1999, it was branded as the world's first GPU. The gamble paid off temporarily. But by 2002, Nvidia's balance sheet was bleeding. A lost Xbox contract and delays in shipping new chips sent cash reserves plunging below $200 million. The company posted a $75 million net loss that year. Securities and Exchange Commission filings from the period describe emergency board meetings, a 25% cut in operating expenses, and the appointment of a turnaround chief financial officer. Survival was not guaranteed. Every engineer, every executive, every board member knew that a single misstep could erase the company from the map. The culture that emerged, paranoid and relentless, willing to stake everything on one big technical bet, would define Nvidia for decades to come. In 2006, Nvidia released a toolkit that would quietly redraw the boundaries of computing. CUDA began as a side project, a set of software instructions that let programmers tap into the raw parallel power of a graphics card for tasks far beyond rendering polygons. The launch documents described it as a tool for researchers, not game developers. The industry shrugged. But in university labs, CUDA landed like a secret weapon. At the University of Toronto, a small group of computer scientists saw potential no one else did. They weren't building games, they were chasing an old dream to teach computers to see. By 2011, their experiments with CUDA accelerated neural networks were producing results that CPUs couldn't touch. Training times for deep convolutional networks dropped from weeks to days. The code was rough, the hardware jury-rigged, but the speed was undeniable. In 2012, their model, AlexNet, entered the ImageNet competition, a global test of machine vision. Trained on Nvidia GPUs and written in CUDA, AlexNet crushed the field, cutting the error rate by half and shocking the AI community. The victory was so decisive that it forced the world's top labs to rewrite their playbooks overnight. The official paper listed CUDA as a foundational tool, and the citation count exploded. CUDA's 2006 release had been a technical curiosity. By 2012, it was the backbone of every serious AI lab. Adoption spread from Toronto to Stanford, MIT, and Google. Nvidia's own internal memos began to describe CUDA as the company's true moat, a software lock-in that would bind researchers to Nvidia hardware for the life of their models. The numbers told the story. GitHub tracked a fourfold rise in CUDA projects between 2012 and 2015. By the end of the decade, more than 85% of top AI papers cited CUDA-based code. What started as an accidental architecture had become the core infrastructure of a new industry and the foundation of Nvidia's coming monopoly. Inside Nvidia's headquarters, strategy meetings took on a new urgency after the CUDA breakthrough. Senior executives pored over internal memos and market data, weighing how to transform a technical advantage into lasting control. The answer was discipline. Year after year, Nvidia kept research and development spending above 20% of revenue, a ratio almost unheard of in hardware. Board presentations from 2013 and 2015 show a company doubling down even as competitors pulled back. Every new GPU generation shipped with a cost-free CUDA toolkit, removing any price barrier for researchers and startups. The software wasn't just a feature, it was bait, designed to make Nvidia hardware the default for anyone building an AI. By 2017, the numbers told the story. GitHub tracked thousands of new CUDA-tagged repositories each year. Internal dashboards at Nvidia mapped the spread. More than 85% of top AI papers cited CUDA-based code, and every major deep learning framework, including TensorFlow, PyTorch, and AlexNet, relied on CUDA as their core engine. The company's own engineers described this as a switching cost moat. Migrating a production-scale model to a rival platform like AMD's ROCm or Intel's oneAPI meant not just rewriting code, but risking months of delays and millions in lost productivity. A 2017 cost-benefit analysis estimated that moving a billion-parameter model off CUDA would require at least $15 million in engineering labor, with a 20% performance penalty. The free tooling policy was no accident. Nvidia's senior strategy staff viewed it as a deliberate investment, a way to lock in customers for the life of their products. Each new CUDA release deepened the dependency as more libraries, drivers, and performance patches accumulated. By the time the AI boom hit full force, the company's moat was visible in the numbers: a persistent 20% plus research and development spending, a global developer base trained on CUDA, and a software stack so entwined with Nvidia hardware that alternatives seemed economically irrational. The groundwork was set. The company's dominance was no longer just technical, it was structural, embedded in the very fabric of the AI economy. Nvidia's financial transformation can be measured in numbers that once seemed unimaginable for a chip maker. In 2024, Wall Street screens flashed a valuation just over $3 trillion, putting Nvidia in a league with the most valuable companies in history. The engine behind this ascent was not gaming or automotive, but the data center, a single revenue line that ballooned from $3 billion in 2015 to $47 billion in 2024. This is not a story told in vague trends. It is written in the line items of SEC 10K filings, where the data center segment now accounts for nearly 90% of total revenue. The source of this surge is the H100 GPU, a piece of silicon that sells for $25,000 to $40,000 per card, depending on memory and configuration. Each unit is spoken for months in advance, often through pre-purchase contracts that stretch into the hundreds of millions. CFO commentary in earnings calls describes a backlog so deep that even the largest cloud providers face rationing. Analysts estimate that a single hyperscaler's order can exceed $1 billion, and the waiting list for H100 cards has, at times, outstripped the total annual output of TSMC's most advanced lines. The numbers are stark. In fiscal year 2024, Nvidia's total revenue reached $47 billion, with the data center division alone eclipsing the combined revenues of AMD and Intel's AI segments. The average selling price for an H100 is now higher than the median annual salary of a software engineer in Silicon Valley. The company's market cap, once a rounding error next to the oil majors or big banks, is now a barometer for the entire AI economy. Every quarterly report, every upward revision, is dissected by analysts for signs of supply strain or demand slack. The valuation rests on a simple premise: as long as the world's largest models need Nvidia's chips, and as long as those chips command five-figure price tags, the company's grip on the market remains unchallenged. But beneath the surface, the scale of these numbers reveals a growing dependency, one that links the fate of the global AI boom to the fortunes of a single supplier. At the height of the AI gold rush, tech giants scrambled for Nvidia's data center GPUs, each move tracked in billion-dollar pre-purchase deals. Microsoft put down $485 million for 20,000 H100 GPUs, locking in not just hardware but a foothold in the next generation of Blackwell chips. Amazon, Google, and Meta followed with their own commitments: $750 million, $620 million, and $630 million, each trying to carve out a guaranteed slice of a supply chain that was already stretched thin. These were not just numbers on a ledger. Each H100 drew 300 watts, and the combined pre-orders from the four biggest buyers, close to 50,000 GPUs, demanded 15 megawatts of power, enough to light up a small city. Data centers scrambled to add new floors, overhaul cooling, and negotiate energy deals just to keep up. OpenAI's disclosures put the scale of dependency into sharp focus. Training GPT-4 required 25,000 A100 GPUs running non-stop for months. At $12,000 per card, hardware alone cost over $300 million, with total infrastructure easily doubling that. The chips were not swappable. Nvidia's CUDA stack ran so deep that moving to another platform meant rewriting millions of lines of code and accepting a 3- to 4-fold performance hit. Supply was not distributed, it was rationed. Cloud providers and AI labs prepaid for years of capacity, gambling on their place in line. Waiting lists stretched beyond what even the largest operators could absorb. The result was a global compute bottleneck, with the hopes of the world's leading AI projects pinned to a single vendor and a fragile supply chain. October 2022, the U.S. Bureau of Industry and Security introduced export controls targeting advanced computing chips. The language was clinical. Any processor exceeding 600 gigabytes per second of memory bandwidth or designed for AI training now required a license for shipment to China. Overnight, Nvidia's A100 and H100 graphics processing units were reclassified as dual-use goods, their sale subject to national security review. Internal filings reveal a direct financial hit. The company reported a loss of $350 million in expected revenue after the first round of restrictions. By 2023, Nvidia's 10K filing spelled out the impact. China, once a growth market for AI accelerators, was now a regulatory minefield. Senior Commerce Department officials described these chips as strategic assets, linking their export to broader U.S. policy on technological supremacy. Board minutes from the same period capture the tension. Executives debated whether to design lower-spec chips for China or abandon the market entirely. Every new rule from Washington forced the company to revise forecasts, reroute inventory, and justify lost sales to investors. The graphics processing unit, once a tool for gamers and researchers, had become an instrument of statecraft. Its allocation shaped not by market demand, but by the shifting priorities of global power. Nvidia's dominance in AI hardware is reflected not just in sales, but in the numbers that circulate among industry analysts. By late 2024, Nvidia holds between 80 and 95% of the global AI training chip market. Reports from Omdia, Gartner, and Deep Research all land on the same reality: 4 out of every 5 AI data center GPUs come from Nvidia. AMD and Intel, once major players, now cling to single-digit shares. But the real barrier isn't just hardware. The CUDA software stack, refined over nearly 20 years, forms a moat few rivals can cross. Every major deep learning framework, PyTorch, TensorFlow, and JAX, runs on CUDA. Migration studies from 2023 and 2024 show that moving a billion-parameter model to AMD's ROCm or Intel's OneAPI costs at least $15 million in engineering, months of lost time, and up to a 22% performance hit. For most labs, switching is simply not an option. Antitrust tools built for old monopolies falter when the real lock-in is software, not contracts, and the cost of leaving is so high. Every advanced Nvidia chip, the H100, the B200, even the custom H20 for China, begins life as a silicon wafer at TSMC's foundries in Taiwan. There is no backup. Internal allocation reports from 2024 show that over 98% of Nvidia's highest margin GPU chips are fabricated on TSMC's 5nm process. The entire AI economy, from cloud hyperscalers to defense contractors, depends on a single island's uninterrupted output. This concentration is not theoretical. A Pentagon-commissioned scenario leaked in 2025 modeled a 6-month blockade of the Taiwan Strait. The result was that GPU shipments dropped by 40% in 3 months, with a projected $2 billion in revenue loss for Nvidia and cascading delays across every major AI project. Even a 1-month fab outage could delay 15% of H100 inventory, costing over $1 billion in missed sales. Earthquakes, political standoffs, or a sudden export freeze all threaten to choke the supply of chips that power the world's largest models. Strategic planners inside Nvidia and at the world's largest data centers treat TSMC as both a lifeline and a single point of failure. Every board-level risk analysis circles back to the same question: what happens if Taiwan goes dark? The answer is stark: there is no plan B. The global AI boom rests on a supply chain balanced on the edge of the Taiwan Strait. Jensen Huang stands apart in Silicon Valley's gallery of founders. For 30 years, he has run Nvidia with a singular grip, refusing to hand over the reins or dilute his vision. Huang's signature leather jacket is more than a branding flourish. It is a symbol of ownership, reinforced by his personal stake of nearly 3% of the company's shares. In an era when most tech giants rotate chief executives every few years, Huang has remained at the helm since 1993, steering Nvidia through every crisis and windfall. His approach is relentless and personal. Board minutes and employee accounts describe a leader who obsesses over product details, meets with engineers deep into the night, and signs off on billion-dollar bets without hesitation. This alignment, skin in the game at a scale few public CEOs ever risk, has shaped the company's culture of audacity and paranoia. The market too reads Nvidia through the lens of its founder. Analyst notes routinely cite Huang's presence as a reason for confidence or concern, tying the company's agility and appetite for risk directly to the man in the leather jacket. At 9:31 a.m. on January 20, 2025, a press release from DeepSeek set off a chain reaction that ricocheted through global markets. The Chinese lab claimed it had trained a GPT-4 class model using just 12,000 Nvidia graphics processing units, half the hardware count analysts expected for that level of performance. Within minutes, Bloomberg's ticker showed Nvidia shares plunging from $237 to under $200, erasing $600 billion in market value by the closing bell. It was a 17% drop, the largest single-day loss ever recorded for a U.S. company. Trading desks scrambled as sell orders triggered algorithmic cascades. On forums and trading floors, the question echoed, if one breakthrough could cut the chip count in half, how secure was Nvidia's pricing power? For months, the company's valuation had rested on the premise of inelastic demand and endless scarcity. The DeepSeek announcement shattered that illusion in a single morning, exposing just how quickly the world's most valuable monopoly could be repriced. Blackwell arrived not as a quiet update, but as a calculated counterstrike. Nvidia's official benchmarks claimed a 2.5 times leap in training throughput over the H100, with each B200 card packing 208 billion transistors and pushing memory bandwidth past 3 terabytes per second. The company's order books filled before the first chip left the fab. Pre-purchase agreements from Microsoft, Amazon, Google, and Meta alone exceeded $5 billion, locking in tens of thousands of units and reserving a quarter of TSMC's 3-nanometer capacity through 2026. For cloud giants, Blackwell was not just a performance upgrade, it was a bet on continuity, a hedge against both technical disruption and geopolitical uncertainty. The CUDA software stack, now deeper than ever, ensured that switching costs for large-scale users would only rise. Yet the question lingers, is this the oil embargo moment for AI compute, where supply is power and scarcity shapes the map? Or does the next breakthrough, whether algorithmic or geopolitical, threaten to redraw the lines overnight? The Blackwell launch answers with overwhelming force, but not with finality. Nvidia's share of AI training chips still hovers above 85%, its $3 trillion market cap shadowing entire industries. Each GPU sold shapes not just corporate balance sheets, but the geopolitical balance of power. The world's most advanced AI runs on hardware that answers to one company, and for now, one nation. Is this concentration of power a fleeting anomaly or the new operating system of global capitalism? Share your perspective below.